In the last video, we came up with the equations we need to calculate thermal stresses when we have a symmetric laminate. And here's our problem statement. We've got a symmetric laminate. It's also balanced between we have plus and minus 30-degree layers and some 0-degree layers as well, 20 thousandths of an inch total of all of those. And again, they're arranged symmetrically. And the temperature change is minus 150 degrees F. As we noted last time, it's pretty typical to have a negative temperature change. If you cure at an elevated temperature, then you have the resin kind of flowing until you reach that temperature, but then the cross-linking occurs up at that elevated temperature, and that becomes the stress-free temperature. So when you cool back down to room temperature, you lock in some stresses, and that's what we're going to try to calculate here. Alpha 1 and alpha 2 are the values for carbon epoxy that are in the summary pages. And you notice alpha 1's very small, and in some references it's slightly positive, others I've used one that's slightly negative. But in any case, it's very, very small, 0.17 times 10 to the minus 6. Whereas in the transverse direction, alpha 2, it's over 15 times 10 to the minus 6, which makes sense that the fibers are not going to contract or extend much with the temperature change, but the resin will. And for comparison, you might remember for steel, the value for alpha was about 6.5 times 10 to the minus 6, 1 over degree Fahrenheit, and for aluminum about double that. So again, these numbers are pretty small for 1 and pretty large for 2. So remember, we had this equation to be able to calculate alpha x, alpha y, and alpha xy in global coordinates. And so for each layer, we're going to use alpha 1 and alpha 2 and the sines and cosines of each individual layer. And so here's what we come out when we plug those values in. You can see for the 30 and the minus 30 that it's the same values for alpha x and alpha y. But if we put a temperature change, one of them is going to shear one way and the other one's going to shear the other. So our alpha xy's are negative signs. And of course for 0, they're the same as alpha 1 and alpha 2. Now we need to calculate the A matrix and as well as the thermal loadings. So for that, we'll need the Q-bar matrix for each layer. And we've seen these numbers before from previous examples. For carbon epoxy, plus 30. Minus 30 is the same except for the 1,6 and 2,6 values, which are negative. And for the 0-degree layers. All right, so now let's look at int of x thermal. What we're going to do is for each layer, take the first row of the Q-bar matrix, multiply by alpha x, alpha y, and alpha xy of that layer, and then multiply that by the thickness of that layer. We'll sum those up for all 3 layers in this case, and then multiply by the temperature change of minus 150 degrees. Now the numbers work out a little easier here. Instead of having to write out the 10 to the 6th and 10 to the minus 6, the Q-bar matrix are usually written in millions, so 10 to the 6. The alphas were 10 to the minus 6, so those will cancel each other out in all of the terms, and so I can write it a little more compactly because of that. So here's Q-bar 1,1 times alpha x, Q-bar 1,2 times alpha y, Q-bar 1,6 rather times alpha xy for the plus 30s, multiplied by the thickness. Then same thing for the minus 30s, same thing for the zeros. And then all that sum gets multiplied by the temperature change of minus 150 degrees, and we come up with minus 37 point something pounds per inch. And you know, the units of that are the same as the applied stress resultants, int of x, int of y, etc. And if we do a similar thing, notice that the ints of yt is even larger than ints of xt, and that ints of xy, because we have a balanced laminate, that's going to be equal to 0. All right, so we assemble the A matrix as we've done in previous examples, and that should actually be the A inverse matrix. I left off my minus 1 there. But we'll take that A inverse matrix, multiply by the loadings, including the thermal loadings. Now in this case, Nx, Ny, and Nxy are all equal to 0 because we don't have any applied load. But if we did have applied loads, they just go into here. We add these thermal loads that we came up with just a little bit ago, and both those are negative. And so here are the strains, the laminate strains. And notice a couple of things out of there. With this negative temperature change, we actually have a positive epsilon x and a very large epsilon y that's negative. Now that would be in the direction we expected it to be. That is, a negative temperature change results in shrinking in the y direction, but actually expansion in the x direction. We'll get into that in just a little bit more. Let's take those laminate strains, and for each layer we can use the transformation matrix T2, and there are our strains now in local coordinates. Now one thing to remember though is that these are total strains, and so remember that the mechanical strains are the total strains minus the free thermal strains, because it's only the mechanical strains that are associated with stresses. And so for each layer, we're going to take the Q-bar matrix and multiply by the total strains minus the free thermal strains. I like doing it in local coordinates because, again, you have a 0 one down here, and you're always working with alpha 1 and alpha 2. And so for the 30-degree layers, we come up with the stresses as shown. So about 4,000 psi compression in the fiber direction, 1,600 psi tension in the transverse direction, and a shear stress is shown here too. Now I should point out these stresses are not insignificant, especially when you look at sigma 2, and remember that the strength in that direction is only about 7,000 psi. So before we've even put any load on it, we've got it stressed to a level of 1,600 psi, and of course if we add loads to it, that's just going to add to that stress. If we do the same thing for the negative 30s, then again the only difference would be the sign of the shear stress. And for the 0 degree, we'll see that it's under tension in both the fiber and the transverse directions. Now just as a check, if we transform these into global coordinates with the T1 inverse matrix, here's what we get for the plus 30s, the minus 30s, and of course the zeros. Don't transform at all because it's 0 degree. And if we remember that the definition of the stress resultants, mechanical stress resultants, is to take the stresses for each layer, multiply by the thickness, and sum those up. If we do that, then we find out that n sub x, n sub y, and n sub xy are indeed 0. Remember, there were no applied loads, only a temperature change, and so n of x, n of y, and n xy are all equal to 0. Now we can also calculate the thermal coefficients of the laminate. And remember, for doing that, we use the inverse A matrix, the thermal loadings, n sub xt, n sub yt, etc., and divide those by the temperature change, multiply by the A inverse matrix. And here's what we come up with for those thermal coefficients. Now you can see in the x direction it is negative, and it's larger than it was for just the 0 degree fibers. And in the y direction, it's more like what you would see for a metal, 8 times 10 to the minus 6. So again, the laminate will shrink in the x direction when it's heated. Now again, being able to tailor that property is not such a bad thing. I remember when they were working on carbon epoxy tubes for the space station, one problem was, one side of it would get the heat from the sun and the other would not, and so having a thermal coefficient that could be tailored to be almost exactly 0 would keep those tubes from bending. And again, we have a balanced laminate, so alpha bar xy is going to be equal to 0. And just out of curiosity, if you want to look at just the angle ply, a plus or minus theta, balanced laminates, you'll see that for fiberglass epoxy and carbon epoxy, they're quite different. And in fact, if the carbon epoxy plus or minus from 0 up to about 42 degrees, you're going to have a negative value, and that negative value it has a maximum magnitude of about plus or minus 30 degrees, like the laminate that we had here. However, the mismatch wasn't so bad here because we had our plus or minus 30s and a zeros. If we had plus and minus 30s with 90s, we'd have a much higher thermal mismatch, and so the residual stresses would be greater. Okay, before we wrap up here, I want to shift over to the spreadsheet where we can add those calculations. So right here under loading, I've added a temperature change right here. And so down below the inverted A matrix, I've had to move the strains down a little bit because the first thing I have to do is to calculate the thermal loadings, n sub x, n sub y, and n sub xy with the equations that we've shown in the PowerPoint so far. But for all of these, what we've done is take the Q-bar matrix times their alpha x, alpha y, alpha xy terms and come up with the terms of the thermal loadings for each layer and then sum those up into n sub x, n sub y, and n sub xy thermal. Then if we have some applied loads, we don't in this case, we would add them here. In other words, the values that we put in here would get added to the to the thermal stress resultants. And with these, now we can use the inverted A matrix and calculate the strains by multiplying the inverted A matrix times the total n sub x plus n sub xt. Now it gets a little more complicated over here because we have to take these strains and convert them into, first of all, into the local coordinates, epsilon x, epsilon 1, epsilon 2, and gamma 1, 2. But then for the mechanical strains, we have to take those total strains and subtract off alpha times delta t. And so those become our mechanical strains. We can then multiply those by the Q matrix and get our stresses and then transform them into the x and y coordinate system just as before. All right, so that kind of wraps that up. And again, we've been working with symmetric laminates for the last couple of sections, and now we're going to extend that to general laminates. One thing is we're going to look at all the loadings simultaneously. We can have in-plane loading, we can have bending, and we can have temperature change. And we can apply that to either symmetric or non-symmetric laminates. And we'll get to that next time.